Alright, time for another DraftPhysics.com, debatephysics.com also. Video presentation. Kinetic energy versus momentum. So it's really Leibniz versus Newton. Okay, so you're either a Leibnizian or a Newtonian. And there's, let's see, we just say there's a couple of simple experiments that are the focus of the situation. You could say that combining, alright, two masses, you give one a velocity, and that they combine into a double mass, okay, with 1/2 of the velocity. Alright, that ends up being short 1/2 of the kinetic energy. So half the kinetic energy is lost. And it's really a mathematical loss. I mean, you just can't evade it, no matter how perfectly you combine the moving object with the non-moving object, that is, you combine the masses. You're stuck, with just a mathematical fact that the momentum can't increase. So you're stuck with an object that mathematically says it has to have less energy. And there is really no explanation. People can say there's deformation or there's sound or the energy leaks into some part of the environment, but it would have to leak into the environment without losing any momentum. So it's like a bowling ball hitting a pin without losing any of its momentum. Energy is exchanged. Energy isn't created. So it's a problem. That's a paradox for the Leibnizians. Okay, and then the Newtonian problem comes in when you do, let's see, I have to think about the experiment. Yeah, you're going to hit a 1 mass into a 2 mass. Okay. And you're going to end up with an amount of energy that comes out, an amount of momentum that's going to increase. So this, the velocity is going to be 3/4 instead of half. So you're going to move something twice as heavy, and you're going to give it more velocity. It's going to retain more velocity than it should. So if you started with 100 momentum worth of energy, you'll end up with 133 and 33 going back this way. And okay, that mathematically works if you do this subtraction thing, but the fact is, in other circumstances like the Newton's cradle, all of the energy goes forward. So you end up with a circumstance where the 1 with the energy hits and the 2 and the 1 end up it's end up being real motion in the universe. And in the case of the coupled oscillator, okay, you end up with it all going theoretically in the same direction. So you can't use your subtraction math, and you just end up creating free momentum. So that's where we are now, is this idea that you can couple two objects. We'll just make them different sizes for the purpose to demonstrate. And what you'll end up with in this experiment is, if you put the energy in this way, you'll end up, let's say 100 momentum, and then this one acquires the energy. It'll acquire 150 momentum. Alright, and then if the energy comes back this way and goes back into this object, it's back to being 100. So you create momentum, then you destroy the momentum, then you create the momentum, and you destroy the momentum theoretically. So that's the experiment I thought would clarify things, and apparently it's got the same problem. So I guess underlying all this should be some understanding that in nature, reality, it's easier to combine things than to separate things. It's easier to make things fatter than it is to make things thinner. So yes, gaining weight's easier than losing weight. And the same is true for velocities. Velocities, higher the velocity, the more structure you need to create the higher velocity. Let's say the more it needs more processing. It's easier to create a heavy thing going slow than it is to create a fast thing, a light thing going fast. So it's almost a thermodynamic, or it's almost one of those kind of issues. It's just a fundamental problem, because gravity is at the core of all this in charge, and those mechanisms are all oblige things to be more attractive than repulsive. Alright, so we're at this experiment, and so there's different ways to do it, obviously. Well, it's not obvious, you have to sort of explain the differences, but anyway. And so the problem is in dissecting where this phenomenon is coming from. Is it real? Is Leibniz right that you can create free momentum to keep kinetic energy balanced? See, in this case, the Ke ends up being balanced. It's the same amount of Ke going back and forth, but you have a very different amount of momentum. In the other case, you have the same momentum, and you have a different amount of Ke. So I'm just saying that's the duality and the paradox that, frankly, I think has to be resolved as one is an illusion. You're being fooled because you're not following all of the variables, and one of them is real, is what physics really is, and you just miss something. So obviously this experiment is a lot more complicated, a lot more parts than just banging, okay, just adding two weights, a 1 plus a 1, sticking them together and ending up with a 2. That's a lot simpler than this is. So there's lots of places you could make an error. So I would just say to anyone doing the experiment, the first thing you got to do is make sure these points are rigid. Okay, the fulcrum is critical. That's essentially what it is, and it can't be doing any exchanges, can't be doing any shifting or bending, any kind of flexing. And so you can sort of understand that the flex inside of a material, like a piece of plastic or something, could be a tiny little bit of movement, but it's a very fast movement. So it can store an awful lot of energy, and you can see that with if you take a complex pendulum, with more than one bob on it, you can create all kinds of oscillation. Tiny little movement up here can create all kinds of motion down here. So these points have to be rigid. So you have to make sure you have these fixed, that this thing doesn't move itself and that this thing doesn't flex, because obviously that will transfer energy back and forth and hide energy. So you're trying to find all the places where any energy could hide, where it could be stored. Okay. And then the other part of the experiment is, once you've established these two are independent, I mean, ideally, there's not even an ability for them to be connected to each other. They're secure to things so distant and so rigid that they can't possibly know about each other's existence. But anyway, and then the next step is to have some mechanism to connect the two. That is some kind of tension mechanism that's subtle. Every time this moves a certain distance out, then this one gets a little tug of the energy, and so they can push on each other and make each other, transfer energy in little pieces. And the idea is that if you do that in some harmonic way, that all the energy will in fact go from one object into the other object, and it'll do a lot of moving, and then it'll go back into the other object, it'll do a lot of moving. And if there is no other place to store the energy, then you have to argue that you've transferred all of it. Now the problem here is this obviously will move up and down at a pretty good rate, whatever this weight is. Now I've seen it with a paper clip, which doesn't seem like it could add much weight and that it could gain much momentum, but it is something to consider. Now I was thinking ideally it might be best to attach the mechanism to the weights themselves. Then you're taking no risk of this kind of event, where you're putting tension that ends up lifting the weight instead of giving it velocity. The weight is, the energy is being stored as altitude. You did work to lift it, and because this line will obviously be shorter, the pendulum gets shorter if it has a kink in it. The actual real distance gets shorter, and therefore it has to go higher, and that's storage. So anytime that's happening, and especially if the kink's in a place where it's in its neutral condition and you put a kink in it this way, you can understand that now you've lifted it and lowered its velocity as it might go through its, for example, a timing gate. So the ideal, so the way I would do the experiment is first establish that you have nice solid points, and then you figure out where your straight line is, okay, and that's where you're going to put your timing gate, where the straight line is. All right, then attach your your binding, the coupling, okay. And ideally, okay, it shouldn't cause any hard tension until this object swings past this neutral point. So there shouldn't be much pressure when they're in their neutral point, and there should be, the pressure increases as they go further out. So what you're basically trying to do is create a circumstance where this one is in this position and this one's in this position, and it pulls on the other one and gives it its energy. This pull is the right word to use in this context, but clearly it's always a push. But anyway, it's an inverted push. Alright, so I guess I'd still argue that ideally it'd probably be best to tie the two things together to the objects, because then you have no chance of bending the pendulum or changing their position when they go through the gate. Their straight line is always maintained, and so the arc is always maintained. So there's nothing that can disturb the arc that they're traveling at. They can never be lifted. And so so you don't attach the mechanism till you've established the centers, and then you attach it, and then if you're going to add energy, the best way to add the energy is from this direction, because then you won't be pulling this out, straightening this line, and giving this one altitude, creating more energy than what you're trying to put into the system. So this height is what you want to be. The only energy you're putting in is this gravitational potential, and if you do it by pulling this one over, then you've added more gravitational potential that you might not be measuring here, but will be in the system. So if you pull it this way, at least you won't be moving this object because you're putting less tension on it. And so when you initiate the action, it'll be all the energy there is going to be this action. There won't be any other source of momentum. Let's see, anything else? Not much. So interesting, the outcome, dissecting exactly where the Newtonians would argue there has to be a storage device in here somewhere. You can't make free momentum, and you can't destroy momentum, so it must be hiding somewhere, this 50 that you're playing with, this extra 50 in momentum. So obviously the source in one case, so if you do it the opposite way, that is, you initiate the energy into the 2 mass, the heavier mass, then you're guaranteed to lose the energy, and you might get it back, but you'll never gain this extra 50. You could have 100 in, and you'll end up with 50 over here, and then you get your 100 back. But you won't have the case of the opposite side where you put 100 in, and then you end up with 150, and then you go back to 100. So it won't have the creation of the free momentum. But again, the free momentum might just be a consequence of the fact that to give this altitude, you gave this one altitude, and that's where the extra 50 is in the extra energy that the other Bob got from being elevated by you elevating this one. All right, yeah, so I think that covers the stuff that I thought of that could be a possible problem. It just doesn't, in the experiment I have seen, it's a kind of a flimsy little piece of wood used, but it doesn't seem flimsy enough, but who knows. And again, the paper clip as the weight doesn't seem like enough weight to store 50 momentums, and that's a lot of momentum to store in a little paper clip. So it doesn't seem likely there's that much energy stuck in the movement of the paper clip. So we'll see if they pursue doing the experiment, making some changes, fiddling with it, and such. And so I think that's probably enough of a video. So, we're sort of, so the evidence is paradoxical, just a fact. Can't go anywhere to any authority and get the right answer. They just give you jargon. So, in the case of the disappearing kinetic energy of the simple card experiment, they just say the word deformation. They don't show you any evidence at all that anything deformed, or that anything got hot, or that any of this stuff happens that could justify losing half the energy. And you can use it in kind of an extreme case where you have a 5-ton train and you add 5 tons to the train. So you're talking about a lot of momentum has to disappear. When you're talking about half of its kinetic energy, you're talking about a lot of energy. So it's so far so bad in terms of finding something definitive to clear it all up. So far the experiments are contradictory and leave it still ambiguous in terms of being able to make a solid argument in either case. I guess I would say that collectively the evidence pool suggests momentum is conserved. It certainly is conserved in space. It's certainly what objects in space recognize is encounters with things with momentum. They don't recognize encounters based on kinetic energy. They're moved by momentum. They're not moved by kinetic energy. So that's a pretty good piece of evidence. The fact that they've never demonstrated it taking 16 times the fuel to go 4 times as fast, or that something going 4 times as fast does 16 times the damage, that is, crushes 16 times as much. Certainly they've come nowhere close to demonstrating any of that. And so we'll see. What we need is more people involved in the conversation in some sort of technical matter, where they do a force diagram and explain where they think the energy is hiding or how the event takes place, but they just won't do that. They won't explain in any, show an arrow where, when the one car with velocity hits the other car and combines with it, then this happens, and show the arrow where it goes, so I can see if I can measure that, that disappearance. See if I can find the energy they say dissipated out of that system. Anyway. Alright, so that's probably enough of a video. So we're stuck for a while. I'm getting a little better, so soon, hopefully, I'll be able to put a couple of pendulums together and play around some more, and we'll see what we get and such. The clay experiments, I'm also thinking about them, and I do have this stuff, and I'm just thinking of different ways of making sure that you compress it in a mold or a form, a little jig, where it's always compressed the same way, so you end up with the same piece of clay. And then the simple truth is that you can use a nail or some other mechanism, as long as it goes far enough in, all the way in. It's a pretty good way to test how much energy there is. You can kind of feel it when you push something into clay. You can kind of feel it doesn't get any harder to push. The first little bit is just as hard as the second little bit, as the third little bit. So it probably is a pretty reliable way of measuring or extracting energy from an object, is to basically push something into it, and because it's basically a fluid. And what you're really saying is, if I drop, like I say, if I make a thick shampoo, right? They used to have this in the shampoo commercial. They'd drop a little steel ball and it would slowly fall through the shampoo, and it always fell at the same rate. Okay, it doesn't go faster or slower depending on how far it's gone into the shampoo. And you're basically kind of arguing the same thing with clay, is that you're displacing it, and it takes the same energy to displace it. And so, in a theory, okay, it squishes pretty consistently in terms of the amount of energy needed per inch or per centimeter or per millimeter to penetrate it or to compress it, compact it, or reshape it, let's just say. Alright, so so there's probably could be some modifications to those experiments that might make them more illustrative of the truth. Okay, yeah, so we'll see. It's just no point in stating it. I'm clearly on Newton's side, Descartes' side, and Galileo's side. They had a lot of experiments, were very careful, and they didn't find this kinetic energy thing to exist. It's clear that these Leibnizians aren't very proud of Leibniz. I mean, they don't call themselves Leibnizians. They don't call it Leibnizian mechanics. It is kind of strange that they want to steal Newton's name and say Newton thought of it or Newton believed in it when clearly he didn't. So why do they lie about that even? I mean, you have to argue that's kind of a desperate move to lie about probably the most famous, greatest scientist in the history of mankind, and they're lying about what he said and what he believed. I mean, that's kind of shocking. And you'd say, well, why would a scientist do that? I mean, why would they pretend they're on somebody's side who they're directly opposing? That's such a cheat, and it's such an anti-truth thing. It's such an affront to honesty and fairness that you got to wonder: are these people really looking for the truth, or are they really just propagandists? It's a fair question to ask, and I think the only answer is clearly they're propagandists. They're fanatics, they're devotees, they're toadies, but they have no interest in the truth. They just have an interest in sustaining all of our obligation to bow at their totem poles. And that bullshit part of their character is obvious. Again, not a single person defending Leibnizian mechanics has made a single video explaining any of that history, talked about how Newton was wrong, explained why Newton was wrong, showed why he was an idiot, any of that crap. Nothing. It's just so dishonest.